So you made it to video number 4. I'm proud of you. But I'm getting too sentimental, and there's still more math to do. Today's video is about the principle of mathematical induction, which is every bit as scary as you think it is. Don't worry, I'll be with you the entire way, and then let go at the very end. You're thinking about applying to grad school, and might be thinking about how good it'll feel to get that graduate degree, until you realize the only reason that you want one is to find a way to defer your student loans until you learn enough math to actually be useful when you're hired. But your software engineering friend is making $57 an hour because he impressed his uncle with a hello world, and you're still in school trying too hard. One of you might be educated, but the other is gainfully employed. So who's really the winner? Today is about your induction into the Mathematical Hall of Fame. This proof technique is useful for proving statements of the form, for all n in the natural numbers, p of n is true, where p of n is a statement that depends on n. For example, p of n could be the sum of natural numbers, 1 through n, is equal to n times n plus 1 divided by 2. Truthfully, the statement doesn't have to be true for all natural numbers, but it could be any subset of integers that starts somewhere and progresses stepwise indefinitely. Formally, an inductive set is any subset of Z that has a minimum m, and given k is in the set, then k plus 1 must also be in the set. Basically, this is like a staircase, but an infinite staircase, which could be an analogy for the endless ambition of humanity, or just a philosophical construct that does an okay job illustrating this abstract concept. You first show that you can get on the staircase. Then you must show that if you are somehow dropped onto any arbitrary step, you can reach the next step. Someone could probably use this in a self-help book. Let's run through an example. If n is a natural number, then the sum of natural numbers up to n is n times n plus 1 over 2. The first thing we do is establish that this is true for a base case. Because the inductive set is natural numbers, we show the statement is true for 1.
I have to mention something important. Do not forget the base case. Do not forget the base case. Absolutely do not forget the base case. Otherwise you'll fall right into the trap set by the globalists. You'll be seeing green scales appearing from the 4th dimension, and you'll wonder why you ever trusted anybody in power. You'll become the lizard brain monster you always feared. They will hunt you down and transform you into a sheep lizard. You'll be having children grown inside pigs. Is that what you want? Sorry, got ahead of myself. I have passion. I'm tough. I care about your proofs. I care about your proofs.
Sorry about that. Yeah. So the base case is important, but the next step is the inductive step. We must assume p of k is true and show that p of k plus 1 is true. So we start with the sum of natural numbers up to k and assume it's equal to k times k plus 1 over 2. If we add k plus 1 to both sides, we have this. If we rewrite k plus 1 on the right side as a fraction and multiply the top and bottom by 2, we can combine the fractions on the right. If we factor k plus 1 from k and 2, we get k plus 2 times k plus 1 over 2, which looks suspiciously like p of k plus 1. So now we've gone through the base and inductive steps. So p of n is true for all n by induction. You did it. But I'll be honest, it was weak. The process of assuming p of k is true is known as weak induction. To make it strong, we can afford to assume more. We can assume p of k minus 1, p of k minus 2, and so on, all the way down to the base case is true, unless the base case is of course false. So now we have extra tools to completely and utterly destroy any problem in the inductive step. Consider the example. For all natural numbers, 2 raised to the n plus 2 plus 3 raised to the 2n plus 1 is divisible by 7. The base case is p of 1, which is 2 to the third plus 3 to the third, which is equal to 35, which is divisible by 7. For the inductive step, we will assume p of 2, p of 3, and so on through p of k is true, and try to show p of k plus 1 is true. So 2 to the k plus 2 plus 3 to the 2k plus 1 equals 7p for some p, since based on our assumption, it is divisible by 7. You might be tempted to try to multiply by 2 and 3, but this doesn't quite get you to where you need to be. Instead, multiply both sides by 2 plus 3 squared. After foiling, we get 3 squared times 2 to the k plus 2, plus 2 raised to the k plus 3, plus 3 raised to the 2k plus 3, plus 2 times 3 to the 2k plus 1 equals 7p times 2 plus 3 squared. If we subtract the first and last terms, we get 2 raised to the k plus 3 plus 3 raised to the 2k plus 3 equals 7p times 2 plus 3 squared minus the quantity 3 squared times 2 raised to the k plus 2 times 3 raised to the 2k plus 1. The left side looks like p of k plus 1, but the right side still needs some work. If we factor 2 and 3 squared from the last two terms, then we have 2 raised to the k plus 1 plus 3 raised to the 2k minus 1, which is 2 raised to the quantity k minus 1 plus 2, plus 3 raised to the 2 times the quantity k minus 1 plus 1. But the last two terms now look like our assumption of p of k minus 1. So now we know the entire right side divides 7. Thus p of k plus 1 is true, hence p of n is true for all n. With enough practice, you can get to the point where induction proofs are trivial and are left as an exercise to the professor when you turn in your assignments. And if you get really good, you can prove every horse is the same color. Thanks so much for taking the time to watch this video. If you haven't already, please like the video and subscribe for more content. That way my subscriber count grows from k to k plus 1. Share any thoughts you have in the comments below, and I'll see you next time.